Okay, so again, example 6 is going to use similar methods to what we've been seeing. It's all about that relationship between displacement, velocity and acceleration. And here you're given the displacement and you're asked to find the velocity when t equals 1.5. So if we want to find a velocity from a displacement, we are going to have to differentiate that displacement. Right, because the velocity is just the gradient of the displacement as explained in the previous lesson. So we differentiate this term with respect to t, and we've got that it's 3 over 2 times 2t to the 1/2 minus 2e to the minus 2t over 3. Okay, so for the first one we just put the power down, the 3 over 2, and subtracted 1. And here when we're differentiating e, we just multiply by whatever the coefficient of t is in the power, so we multiply by minus 2. Then I'm just going to neaten it up, 3 over 2, sorry, it's going to be 3 because the 2's are going to cancel. So 3 lots of t to the half minus 2/3 e to the minus 2t. And what we'll see is that it's when t equals 1.5, so we need to substitute 1.5 in. So 3 times 1.5 to the power of a half minus 2/3 times e to the power of minus 2 times 1.5 will give us, when we pop that into our calculator, a value of 3.64 meters per second, and that's rounded to 3 significant figures. So all we've done is we've differentiated and we've substituted in. So that part was all about just knowing that definition, knowing that velocity is the rate of change in the displacement. For part B, you might have noticed earlier in the question that it tells us the mass of the particle, 6 kilograms. We didn't use that in the first part, but now it starts talking about forces. So straight away we should be thinking of that formula, F equals ma, right? That formula we use all the time in mechanics because we've got a mass and a force. And obviously we need to work out the acceleration to use that. Now because we've got the velocity, we can work out the acceleration in a similar way. The acceleration is dv by dt, the rate of change of the velocity. So all we're going to do with this is we are going to differentiate using this term here. So this is 1/2 times 3 t to the minus a half, subtract 1 from the power, minus 2/3 times minus 2 e to the minus 2t. So again, I'm multiplied by the coefficient of the power, which is minus 2. I'm now just going to neaten it all up. So this is 3 over 2 t to the minus a half minus, plus, 4 over 3, 2 minuses cancel to make a positive, e to the minus 2t. And then, because it gives us a time, it's when t equals 2, I can substitute in that value. So I pop 2 into there, and then on my calculator I type it in, and I see what I get, and I should get, if I've done it correctly, 1.0850 meters per second squared. Right, we're going to use the acceleration again, so we're going to make sure it's nice and long, lots of accuracy there, so it doesn't change our final answer. So once we've got the acceleration, we're just going to pop that into F equals ma. So the F is just the force it describes here, that's why it says it's a single force, so I don't need to resolve anything. So its F must be equal to 6 times 1.0850, which should give you that you get 6.51 newtons to 3 significant figures. Okay, again, mechanics always put things to 3 significant figures. That's it for that example and for this lesson. So it will be exercise 8C for you to have a go at. Do the odd questions, there's not many, and if you feel like you need more practice, have a go at the evens as well.